Good morning, all of everyone present in this meeting today. Dr. Arvind Kumar, welcome you all on the third day of 5 days faculty development program uh, on manufacturing and automation. Uh, Today's speaker, we have Dr. Anil Kumar Chaubey. Dr. Chaubey is a principal scientist in CSIR-IMMT Lucknow. So uh, I'll have a brief introduction about our college. Um, that our RTC Institute of Technology has started its journey from 2008, and we have a wide range of land. That is 15 acres land we have, and the total courses we are running as a BTech in 5 branches in BTech and 3 branches in diploma. So total altogether 450 intakes we have in our college. So it is situated at Ormanjhi, near the Ormanjhi block in Ranchi. So now I will introduce about our speaker today. Today's speaker, Dr. A.K. Chaubey, sir. Dr. Chaubey, sir, is presently working as a principal scientist, senior principal scientist at CSIR Institute of Minerals and Materials Technology, IMMT, Bhubaneswar, Odisha. He got his BTech degree in metallurgical engineering from BNIT Nagpur and MTech and PhD degree from IIT BHU in metallurgical engineering. He has he has more than 15 years of research experience in the field of mechanical alloying, nanostructure material, powder metallurgy in particular. He has published 40 SCI papers in, uh, and he is a member of various professional societies and actively engaged as a reviewer in many reputed journals. His area of interest is lightweight alloys and composite, nanostructure and functionally graded materials, powder metallurgy, tribology, and electron microscopy. So, with this introduction, I'll hand over the session to our speaker, Dr. A.K. Chaubey, sir. Sir.
Yeah, may I audible to you? Hello? Hello?
Hello, you are audible, sir. You can continue.
Yeah. Thank you, Dr. Arvind, for your nice introduction. And I would like to thank RTC Institute of Technology, Ranchi, for giving me this opportunity to present my work to in front of very large audience. I also thanks to the head of the Department Mechanical Engineering, RTC Institute of Technology, for arranging such a nice program for this faculty development program. So before just give me a time to just share my slide. Hello. Hello, Dr. Arvind, whether this slide is visible? Hello.
Yes, sir. It is visible now, sir. Yes, visible, sir.
In full screen.
Yes, sir. It's visible now.
Okay. So, yeah, good morning to all of you whoever is attending through this program to online. So good morning to all of you. I'm going to present the today's talk is on the advanced lightweight alloys for automotive and aerospace application. So you all, I am Dr. A.K. Chaubey. I am a senior principal scientist at CSIR-IMMT Bhubaneswar. So you all aware about the lightweight material. So I am giving just background of the talk is to just small introduction about the lightweight alloy, and then applications in different field of the lightweight alloys, and then I will explain what are the problems in lightweight alloys and how we can solve these problems to utilize in different field as per design requirement of the alloys. Then I will just give a small introduction about the how these alloys are fabricated in by different processing route, and then I will tell about the microstructure and mechanical property of these alloys, and I will take some case study so that you can know about the clear idea how these alloys are fabricated, different alloys, and how these property can be achieved, and how these are according to the design requirement and application requirement, we can modify the parameters to get the required property. And then finally I will summarize the talk. So now coming to the introduction part, because I'm going to talk on the light alloys, so I just introduce what are the metals, and because the metal is the alloy is the part of metal, and metals are actually the substance which characterized by its different property like electrical, thermal conductivity, reflectivity, ductility, and malleability. So these are the actually property which differentiate the metal from the non-metals. If it is a non-metal, the strong edge is a metal, so it's compared to it is much stronger than the non-metal, and it is a malleable. It is a luster. It has a luster. It has a shining, so that it can you can clearly differentiate the metal with the non-metals. So, and then coming to the alloys. Alloys is actually the mixture of two or more than two elements, and one in that one element should be the actually the metal. And here is example of the copper and zinc. If you see that the copper actually replacing the copper is replaced by the zinc atoms, so it is forming a like a solid solutions of the copper in zinc, and you can get this copper zinc alloy. And this copper zinc alloy has a different depends on the concentration of the zinc. You can vary the different colors of the copper zinc alloys. This is the actually the called is a brass, and in it's called in Hindi it is called a pital. So the color of the brass is also varying with this different composition of the zinc, and the property also vary with this composition, how much percentage you are adding the zinc in this copper. So then why actually this is required to making a alloying in this for a different elements in another metal, so that why it is required? Because it is required to for this because some critical applications or some demanding applications where the property you cannot get by a single metals. That time you have to think how you can get the required property. So in that sense, this alloying is a very much important, and by the alloying you can get the most of the cases you can get the required property. So for the suppose you want to make a high strength material which required very high design strength and for a different engineering applications. So in that case, a single metals like iron, either copper or zinc, you will not get a sufficient strength. So in that case, you are choosing particular elements which can added to a and particular composition and fabrication methods, and then further the processing method and post treatment method, so that you can get a final strength as per the requirement of design design and for particular application. And some modern applications where the pure metal cannot give a property, so you can alloy with other elements. And like a space vehicle where you have required very material should be light, and it should stand very high temperature, and it should have a sufficient strength to, and it should have a ductile to brittle transition temperature should be very low, so that it can sustain in different atmosphere. So in that case, you need a different alloying element to get that property. Bridges, turbines, and in naval application where high corrosion resistance is required, so you have to choose the particular alloying element which is improve the corrosion resistance of the pure metal. And certain times you need a very high reflectivity and high conductivity and high thermal conductivity, so that in that case you have to choose particular alloying element which did not reduce the thermal conductivity or electrical conductivity, so that you can get the required property. And sometimes you need a different for a showpiece or some applications where you need to change the color of the material. So in that case, the alloying is also done. Hello. Hello.
Yes, sir, you are audible, sir.
But whether slide is changing?
Yes, sir, needs of alloying. The present slide is needs of alloying.
Yes, but I'm changing next one, but it is not changing. That's why I thought whether connection is disturbed. Let me just
go to the previous one, sir. Previous slide.
It's also not changing. I think
Now it's changing, sir.
Okay.
Yes, sir.
So now I'm on slide number 6. Actually, this is the role of the alloying element. So what are the roles of alloying element where to get the required property? So if you are adding a alloying element in a pure metal, so it can be either you can choose according to your criteria or your requirement. Suppose if you and it depends on certain rules like a Hume-Rodri rules, where you can add the which particular element can be added in and what should be the composition and what should be the size of the particular metal, so that you can add that one. So in this case, when you are adding and atomic size are quite similar in size, so the one atom is replaced by the other metal atom. So in that case, you get a substitutional solid solution, and the lattice position is actually occupied by the another alloying elements. And in that case, because there is some difference in the atomic size, so that this lattice position is distorted, and that's why it creates a lattice distortion, and that's why the mechanical strength is increased in this case. And when your atomic size which you are adding, which is very small, and it is going to sit on the interstitial space, where this is interstitial space of the atoms, where the another atom is going to sit when it is in very small in size. In that case, you are getting interstitial solid solution, and this actually hindered the motion of the dislocation during the deformation or during the pulling or any kind of deformation. So that's why this resist the deformation and increase the strength of the material. So these are the certain principles which governs the which type of atom should be added in the to get a required property. There are many such kind of rules and many property according to the your requirement. You choose different alloying elements. So our topic actually, it is a lightweight material. So why lightweight is required? Because in lightweight, in case of the automobile, where you are decreasing the weight when you are using the lightweight material for the construction of the vehicles. So and same time many applications for when your material utensil or any articles is lighter, it looks handy and you can carry anywhere. So and also if in case of the automobile, where this fuel consumption and safety features and performance is very critical parameters, when is different reported studies shows that when you decrease the weight of the vehicle around 100 kilograms, so and in for 100 kilograms and 100 kilometer running of the vehicle, so you can reduce the fuel consumption by 0.5 liters. So in this case, when you are reducing the fuel consumptions and effective burning of the fuel, so you are increasing the efficiency of the vehicle, and same time you are reducing the cost of the running of the vehicle. So this case is very much helpful in the case of the vehicle. And nowadays the vehicles weight are similar, but nowadays a lot of features for the safety which has come, and everybody wants that their vehicles should be completely secure and should have all features. So these features actually add the weight of the vehicle. So if you want to add the features, so either you have to choose to reduce the weight of the vehicle to make a complete vehicle weight is similar. So for the constructional items, you have to reduce the weight, because so lot of effort has been done to reduce the actually steel parts, which is a high density and heavier, to by the titanium alloys and aluminum and magnesium alloys. So many components as per the design and the similar strength which we can compare to the steels, which we can replace, that part is easily replaced. And that's why the and also the if you are decreasing the weight of the vehicle, your performance also improve the vehicle part. Here you can see that this base structure of the vehicle, which is from 1975 to 2015 data, you can see that the initial the base structure was very high, around 1500 kg, but it has reduced drastically during the passing of the time, and when the many steel component was replaced by these aluminum and magnesium components, and many composite was also used during these times. And now in future also many component which is still are used by steel material, that are also going to replace simultaneously in coming days to reduce the weight of vehicles, because the every auto companies are looking for to reduce their vehicle weight, and they are increasing the safety features. So here you can see earlier the safety features were very small section, but now the safety features are also increasing, and then comfort and convenience, many things you are added in the vehicles. So this part was earlier very less, but now it has been increasing. So your choice is to increase the base, decrease the base structure as much as it is possible to accommodate the safety and convenience feature. So nowadays, that's why many companies are looking for to replace this steel structure by this aluminum and other lightweight materials. And in aerospace, what are the requirement for this lightweight? Because the aerospace weight is a very critical part, because this aircraft has to fly. So whatever the minimum weight it can be carry, so that will be good for improving the efficiency of the engine, as well as they can accommodate extra weight of passenger weight. So the main requirement is the components should be very light, and it should be a very durable, because the aircraft is running some low temperatures, atmospheric temperature, sometimes little bit higher temperature and different atmosphere, because sometimes it is going to the sea, marine atmosphere, sometimes in the normal atmosphere. So the material should be a very durable and highly corrosive resistance, so that it can sustain in the all the atmosphere, and it should have a high tolerance limit, and it should be have a high fatigue resistance, because this is going to use in continuous operation, and here actually damage tolerance should be very high. Otherwise, the aircraft cannot sustain, and any small fault cannot be tolerable in the case of the aerospace material. So here is a very critical requirement of the property, and there is a same time it should will be also a cost effective solution, so that many company can attract, and they can replace by the lightweight material. And balance of the property is also very much required, because for a critical application, all the property which is required for this aircraft and space, other space applications, they are very critical. So all the properties should be in balanced form. So in this, what are the choice for this to replace this by lightweight materials? So these are the aluminum alloys, magnesium alloys, titanium alloys, and many composites are nowadays are used for this replacing the aircraft component by these lightweight materials. And if you look the chart, which is showing that the what is the weight in the x-axis, you can see the density, which is a weight of the actually represents the weight of the components or the material, and in this side you see that Young's modulus. So initially you can see this is the foam. Foam is a very light porous structure, density is very low, but here Young's modulus is also very low. So it cannot be used for this aerospace and automobile applications for some critical components. It is used for where this actually mechanical property is not a critical, when it thermal conductivity or insulation is required, there it can be used. So after that, you can see the polymers, woods coming to this range. They are not actually the part because this also Young's modulus low, density is low, but Young's modulus is very low, which cannot be used for this purpose. Then comes to the ceramics and metals, which is basically used in metals. The lightweight materials are choice for these actually automobile and aerospace components. And if you look at the how the vehicle weight was reduced by different materials in the time, and the component wise, you can see the main body structure is this is by a green color, and then chassis is by light yellow color, and then blue color is by powertrain components, and the black one is the other safety and comfort, all these part is there. So if you see that the mostly it is a alloy steels, if you look, then advantage of the means this alloy where you can, if you are using the lightweight means alloys for a high strength alloys, then you can reduce up to 19% of the weight of the vehicles. But if you are replacing some of the parts are which is actually can be replaced by aluminium alloys, then the weight you can reduce up to 30% weight of this vehicle. And if you are replacing the parts by magnesium alloys, then magnesium, because it is lighter than aluminium also, and it is a 2/3 of this weight of this aluminium alloys. So you can reduce around 37 to 38% of this weight of the vehicles. And composite also you can replace similar weight. So the composite and magnesium alloys almost similar, giving a weight performance, because the density wise also magnesium is very lower density 1.6, and which is comparable to the composite materials. So the mostly you can see that this aluminium and magnesium alloys in the case of the lightweight alloys are most of the components can be replaced, and they can give a better with this without losing the performance is compared to the steel components. So you can replace the 30 to 40% of the weight you can substitute. So now coming to the general magnesium aluminium alloys, what are the actually the application of the magnesium aluminium alloys in this different field? So you can see that this, because of the magnesium aluminium having a low density and high strength, and which gives a high specific strength of this material, and it is also a good castable alloys, and magnesium is also biocompatible, so that you can use for biomedical application as well. So many applications of these alloys are in transport, where many applications, steering wheels, framework, powertrain, gear housing box, so many application, engine block castings, gear housing box, and this is the biomedical application where can biomedical implants can be made by this magnesium alloys. Aerospace applications, electronics application, you can see because of the lightweight of magnesium, many electronics component were require handy is one of the criteria. Many electronics components was replaced by this magnesium alloys. Apart from this, these alloys are also used, this lightweight alloys, aluminium magnesium based alloys was used for the missile and other applications, photo engravings, deoxidizer and desulfurizer. Anode, because of this magnesium alloys are highly corrosive, so it is used for anode application. And sports and goods equipment, because of this lightweighting, this large sports components are made by this. And I told you that magnesium is biocompatible, so the many bio implants and accessories of the implants are made by this by magnesium based alloys, screws, and this you can see that this is stent and nerve guide, and because these are are biomedical and it is a biocompatible, and only it need to be checked the degradation rate of the magnesium alloys. So many research is going on this area of the biomedical applications. And what are the now coming to the what are the different fabrication method of these alloys? So actually the lightweight alloy is mostly made by this casting process, because this casting is a economical and large volume production can be done by casting method. So the many castings like a sand casting, die casting are permanent mold castings are used for this lightweight alloys, and stir casting and bottom pouring, where you can add some if your alloys are not completely miscible, you can do by stirring and then bottom pouring method, the casting process. And apart from the casting, other powder metallurgy processes also alloys are made because of some immiscible alloys and some heavy metals which is not completely miscible to each one. So that's why many alloys are made by this powder metallurgy method. And and in this case, powder metallurgy, you can extend the solid solubility by mechanical alloying, and so that large volume fraction of the other alloying element can be added in this case. So these are the some processes like a spark plasma sintering process, where spark is created between the two electrodes and the material is placed between the two electrodes, and you can get the uh, sample sintered by spark plasma sintering process, and simultaneously you apply the pressure to get the high densification in the component. After that, this material can be extruded to remove further porosity also. And then other additive manufacturings are 3D printings, where you can get a near net shape by using the powder alloys to get a different components by the near net shape additive manufacturing process. And mechanical alloying is also one of the process for powder metallurgy route, where these different powders can be mechanically alloyed, and the mechanical in this mechanical alloying process you can increase the solid solubility limit, and then after that sintering, either extrusion process, you can make the component by this mechanical alloying powder metallurgy route. So now coming to the what are the selections criteria where you can how you can get these alloys. So in this for the selecting the alloys or making the alloys, the phase diagram is the one of the most important tools or a diagram where you can actually get how much the percentage of this A or B can be added in the parent metal, and what should be the phases of the different percentage at a different temperature and different pressures, so that which gives a guideline to make the alloy. And also you can control the structure and property of this your alloy. So here actually phase diagram is the depend on your composition and temperature of the different alloying elements. Here you can see that A and B is alloyed, and in this range you can see that this is the solidus and liquidus range, and you in between this is this liquid and solid region. So after adding one increasing the suppose this is the copper and nickel alloy, it's a binary alloy, and if you are adding the nickel in the copper, and you are getting the alpha this copper solid solution, and this is the liquidus range, and liquidus range when the pure copper is there, and when you are adding the nickel, your liquidus range is going to higher temperature. And this actually just guideline to see that what phases you are getting at what temperature and room temperature, how much the phases percentage or volume fraction you are getting after the your solidification of the alloy. So in this one, lever rule is also one of the tools where you can get the exact volume fraction of the phases, and in the in certain phases how much the A element or B element is there. So you can get by the Lieber rule. This is the see that this is the one of the alloy phase diagram, and where A and B are there. A is the 100% this and B is the 100% this. This is the iterative point. And suppose if you want to get the composition at this point, this is the W1 composition. So by the W1 composition, you can get by the Lieber rule, where you draw a line parallel to the your x-axis at that, and you can drop a line to a y-axis also, so that you can get the W0, and this by applying this actually the Lieber rule, you can get the your particular composition at that particular point and particular phase. So according to your requirement, you can choose how much the alloying element can be added to get this volume fraction of the phases at different temperature, and also to the room temperature of this. So this is the one actually the guideline how to make the alloys. So in physical metallurgy, many such rules are there, are many guidelines which help you to find out this designing of the alloy. Here I have given just a small introduction. So the what are the automobile solution for the lightweighting of the vehicle? So in the lightweighting, first you should have to choose a lightweight alloy, so that you can replace the lightweight components by using the lightweight alloy. And then after that, you have to see the design parameter of this component, and how you can modify the design for a lightweight design components. And then you have to also see that what are the technology are available, and how you can modify the technology to get this design as well for the lightweight casting or lightweight using lightweight material. So you same times you have to see the design and also the different fabrication parameters, and then what are the technologies are available for this fabrication of these lightweight alloys. So all these you have to actually see for the different, if you are choosing aluminum alloys or if you are going for a magnesium alloys, then you have to see that the first the alloy, how you are going to make the alloy, and then how you are, if suppose certain design parameter is there, so how you are going to get that design of the component, and then what are the technology you have to choose, so that you can get a particular design without any defects or any compromising the property of the material. So these parameters you have to see for a different designing of the different alloys. So after that, I'm coming to the case study part. So in the case study, I'm going to give a case study of the magnesium aluminum lightweight alloy, which is first I'm going to give a synthesis and this alloy fabrication process by this powder metallurgy route, and then I will also explain why the powder metallurgy was used in this process, and how we can modify the disadvantage of the liquid metallurgy by using this powder metallurgy route, and what are the limitations of this by the powder metallurgy route. And then I also certain other case study, I will show you the this alloy, same alloy fabrication by this casting route. So first I'm going to give this powder metallurgy route. So what are the actually the problems in magnesium aluminum alloys? Because the magnesium aluminum, if you look the phase diagram of the magnesium aluminum, so solid solubility is less than 1% at a room temperature of this aluminum in magnesium. So then what happening when if you are going to this certain melting temperature and adding your magnesium in aluminum, and then you are solidifying your to room temperature, then you are getting a two-phase, coming to the two-phase region, where is the alpha and gamma phase. Gamma is actually this magnesium 17 aluminum phase, which is a brittle phase. So this phase is a semi-coherent SCP cubic structure, which is actually incoherent with the magnesium matrix, which is a HCP structure. So, but anyhow, you are getting this phase. So we have to avoid this phase and minimize this phase. Otherwise, our material will become a completely brittle, and the interface between this magnesium and this gamma phase is also a very fragile. So that's why when it is used in a real condition, many cracks are formed when the gamma phase is much more in this this alloy. So our aim is to actually reduce this gamma phase in magnesium aluminum. One way, if you don't use the aluminum, you will not get a gamma phase, but that is the completely alpha aluminum, and you will not get the strength of this alpha pure magnesium alloys, which is very low strength. So, but aluminum is actually most alloying element in aluminum to increase the strength, because it is forming this phase and this increase the strength, but same time it is a incoherent phase, and that's why it is a brittle, make the material brittle. So you have to form the phases, but you have to reduce the volume fraction of this gamma phase, and it is if in the microstructure, the cast microstructure, you can see that these phases are forming. This is the gamma phase along the grain boundary. So our aim is to reduce this gamma phase, as well as to uniform, if this phases can be formed uniformly, it is not only segregated along the grain boundary, then you can get a better property, and you can minimize the this gamma phase effect in this alloy. So what are the solutions for this minimizing the gamma phase? One is this by this mechanical alloying powder metallurgy route, and another is adding the rare earth element. Rare earth elements forms this, actually this takes the aluminum and forms another intermetallic, so that you are reducing the gamma phase in this alloy. So first I'm going to tell you how this you can reduce by powder metallurgy method. So in the powder metallurgy method, actually we are making the mechanical alloying and forming a nanostructural ultra fine grains in this alloy, and then by solid solution strengthening, because this mechanical alloying, you can increase the solubility limits of the aluminum in magnesium, so that most of the more and more aluminum is going in the solid solution. So the aluminum forming a gamma phase will be very less. So that's why you can reduce the gamma phase in this alloy. And then certain gamma phase which is precipitate, which will not be along the grain boundary. You can see the microstructure here. You are not seeing the gamma phase are forms along the grain boundary. It forms uniformly. So that's why whatever the gamma phase, which will be very fine in the nanocrystalline or ultrafine grains, and which is very distributed along the throughout the matrix. So that's why you can minimize the effect of the gamma phase. So I'm going to tell you how this alloy was prepared. This actually, we have added this 7.4% aluminum in magnesium, and by this powder metallurgy route where we did a mechanical alloying by the planetary ball mill, and then this powder was hot pressed and then hot extrusion. After the pressing, you can get this tablet form, and this tablet was again used to for extrusion, and this you can get after the rod form, and then the final property of this alloy was evaluated. So this is the just a parameters which is used. This is the hot press, and this is die where the powder was filled in the die, and then it is heated and pressed, and after that you are getting the pellet, this tablet like this cylindrical, and then this was extruded at the 400-degree temperature, and this 10 mm diameter was initially and it reduced to 4 mm diameter after the extrusion, so that you are getting a very highly dense your final component. So what we have done to reduce the aluminium or extend the solid solubility of the aluminium in magnesium, so that you can reduce the gamma phase formation. So this mechanical alloying was done by 5 hours, 20 or 40. We have gone to 100 hours, and we see that there is a still small gamma phase is here, and then it was again done 3 hours of the cryomilling to make the particle size very small. So, but in this process, because this lot of handlings, in fact, it was done in the actually the handling was mostly done in the glove box, but the certain actually during the processing of the extrusion or compaction, there is some contact of the atmosphere, so magnesium is highly oxidable. Some oxidation is taking place, but these oxides are also very fine and distributed throughout the matrix. So that's why here this you can see that the small gamma phase and the solid solubility, because the aluminium peaks are broadening and the magnesium, so aluminium is going inside the magnesium, and I'm showing here this how the particle size reduction takes place during the mechanical alloying. So initially, because of the ductile material, initially the particles size is increases, and when further when the fracturing takes place, fracturing become dominant compared to the cold welding. So then you are fracturing take place, but the even 100 hours of the hour milling, we could not get the very fine particles. So that's why the cryo milling, because in cryo milling we have reduced the temperature of the vial to around minus 40-degree temperature, average temperature, so that and then it was again mechanically milled. So we get a very fine particles. Why? Because it is a very ductile material. That's why a cryo milling is required for the to get a very fine particles in this case of magnesium aluminum alloys. Here I am going to show you the elemental distribution during the mechanical alloying. This is the 5 hours, 40, 100, and then this is the cryo milling, and this is the your original picture. This is the in this magnesium distribution and the aluminium distribution, and this is the combined magnesium aluminium. These pictures and going this side for different hours. So you can see that the initial period of the 5 hours, this aluminium is not going in the inside the particles and not forming complete solution. It is just covering the particles, and then after the 40 hours, many cracks are forming in the magnesium particles, and the aluminium is going inside. So, and then 100 hours, you can see that this almost inhomogeneous solutions are formed. Most of the aluminium and magnesiums are alloyed, but some parts still remain. So that's why the cryo milling was done, and after cryo milling, you can see the very fine and homogeneously distributed magnesium aluminum particles in this alloy was formed. And then it was hot consolidated by hot pressing and then extruded. You can see the microstructure now. Earlier in the cast structure, you have seen that the gamma phase are along the grain boundary, but here you can see the gamma phase are mostly distributed. You can see here in this color pictures, this elemental distribution map. You can see the aluminiums and this magnesiums are the phases are, and this gamma phase are submicron size, less than 1 micron or 0.5 micron, 0.2 microns size. So that's why this is the aluminium distribution you can see. So here in this by mechanical alloying, we could able to get the aluminium more and more in solid solution, as well as we are reducing the size of the aluminium gamma phase, as well as we are distributing throughout the matrix. Distribution of these particles are going through whole the matrix. So our aim was, which was to reduce, to actually the gamma phase should not be solidify along the grain boundary, and also to reduce the gamma phase. So by this powder metallurgy, this objective was achieved. And that's why in the next slide, you can see how we are getting the, here, this is the STM microstructure, where you can see this, or this magnesium oxide little bit, which is just very fine, less than, it's a very 5 to 7 nanometer and distributed along the particle interface mostly. And the gamma phase are, this the interface is also here you can see are very good. There is no gaps or cracks at the interface. So it shows that this magnesium aluminum, this gamma phase forms in the throughout the matrix, but the interface is also very good. Here you can see this. This is the MgO distribution. For the MgO distributions are also seen. This is a magnesium distribution, and the interface also you can see, and it is a very small size of the magnesium oxide distributions. So this is not doing any harm, but it's just only strengthening the matrix in this case. So here you can see the final mechanical property. This is the, and we have compared the mechanical property with this cast structure with the powder metallurgy structures. You can see this is the mechanical property in tensile. This is the of this magnesium 10 aluminum cast structure, where this gamma phase are along the grain boundary, and this is the actually mechanical property of this powder metallurgy structure, where you can get the 3 times around. Here is 700, here you are around 200. So megapascal, and the ductility almost remains same. So, and after heat treatment, the mechanical property is not going to drastically down. It is around 450 megapascal. So, and still it is a twice, almost twice, more than twice of this this cast structure. So here this shows that the powder metallurgy method, if you can make this alloy magnesium aluminum, so you can increase the you can get your objective to get a higher strength without losing your ductility. So what are the actually reason why we are getting the such a strength of the twice or thrice of this cast structure? So the fracture surface was also analyzed, and in the parent material after fracture, you can see how the cracks are going and is stopped here, and then another cracks are forming, another stopped here. So it's not throughout the crack is going one portion to the other portion, but it is stopping by the certain micro cracks at the tip of the main crack. So the cracks are stopped, and then the another cracks are forming. So it is a delayed cracking. So that's why your this this material we have you are getting a ductility as well as the strength in this condition. So now coming to the magnesium this case study 2, where we are going to form this magnesium aluminum alloy by casting method. The powder metallurgy method, we are in fact we are getting the higher strength, but to get a bigger component and cost economy is another factor. By powder metallurgy method, that is a limitation to make a component, and the cost wise is also is higher compared to the casting alloys. So that's why we have to look another method where we can get the same objective to reduce the gamma phase and increase the solid solubility or strengthening in the alloys. So this we have tried also the casting method. Hello, Dr. Arvind, yeah.
Yes, sir. Yes, sir.
Okay, so I thought no response whether we in connection or out of connection. So okay.
No, sir. We are listening, sir. We are listening.
Okay, if any question in between, you can ask either after that. If you are interested after the presentation, also you can ask in between. If you any query, also you can stop me and I can give a explanation if any required.
Yes, yeah. Dear participants, if you have any question, please put your any query, any doubts in between. Also, you can. Sir has given permission. So, if you have any question, please put a question to sir. Sir, please continue, sir.
Okay, thank you. So I'm going to give this magnesium aluminum alloy production, which is mostly used in automobile and aerospace components. Yes, by casting method. So here actually we have tried first this magnesium and aluminum. So we have used the magnesium 5 aluminum alloy and then added some zinc in this one. And then added calcium also in this alloy to see that how this possibility to reduce this gamma phase in this alloy. And we have produced this one by ester casting method. So where here this you can see this is the furnace and the argon is passing in this to reduce the any oxidation or something, and then melting the magnesium and then adding the zinc and calcium in this one and stirring and then bottom pouring. So the stopper is we have taken out and the melt is going to the mold.
So all these three alloys have been made by the same stair casting method, no, sir?
Yes, yes. All these three alloys is made by these three this method.
Same stair casting method. We have yes. The right side. We are seeing that stair casting setup.
This is the actual furnace, and this is the schematic diagram.
Yes, hopefully I have worked in this.
Yes. Yes. So, and this is the cast alloy you can see, and after the casting the samples. So the microstructure study we have done. So here you can see this is the gamma phase as the casting structure, magnesium 17 aluminum, which is along the grain boundary, which is already I have shown that the magnesium aluminum alloy. This is the problem that this gamma phase is forming along the grain boundary. This is the magnesium 5 aluminum alloy. And when you are adding the calcium, so calcium actually the gamma phase is reduced in this case, and because the Al2Ca, because the calcium forms the another intermetallic phase with the aluminum, that is the Al2Ca phase, Al2Ca, Al4Ca, phase. So these phase are and that's why aluminum is not available for magnesium to form a gamma phase, and this was avoided, the gamma phase. But this is another intermetal it is forming in the case of the calcium. And when you are replacing the calcium by a zinc, so what happening here? This zinc is actually in cut here. Magnesium, aluminum, zinc is another complex metallic phase is forming, and some gamma phase also inside this semi-solid region, this complex phase region. So gamma phase is there, gamma phase volume is reduced, but here this magnesium aluminum complex phase is also forming in this case. So let's see what is the effect of these phases.
Yes.
So here you can see that we have calculated the volume fractions of the phases by this image analysis method. So different this phases was by image analysis. We have different volume fraction was calculated, then added together, and in this phase you can see the gamma phase are around 11%. So this is the phase, this which is the different. You can see the P27, P15, P24. So all points of the points was actually with the help of the software. This was calculated and it is found around 11%. But in the calcium, this phase, this gamma phase was though completely eliminated, but this Al4Ca phase, which is the around 2% in this case, and in the case of zinc, we are getting the gamma phase. Gamma phase is around 1.75%, but another eutectic phase, which is the magnesium, aluminum, and zinc phase, which is much more, around 21% is forming in this case. So here you can see the strength, what is happening on the strength. This is the pure magnesium. This black one is the pure magnesium, and this magnesium 5 aluminum is this one, this red one, and the magnesium 5 aluminum 2 calcium and magnesium 5 2 zinc. 2 zinc is this one, and this is the calcium. So you can see that the aluminum is more effective for strengthening. You are getting more strength when it is only aluminum, but the ductility wise less reduced. So to remove that gamma phase, we have added calcium, but the calcium addition, you can see that this have an effect. It reduced the strength, but ductility also not similar. Yes, so ductility, no improvement in ductility. So because the calcium is having another intermetallic, and that also act as a similar, it also a brittle, and that's why the ductility has no improvement. But adding zinc to 2%, you are getting a better ductility, and you can see that the
strength is also higher than calcium.
So that's why the calcium is not effective in this case. Zinc is effective, but 2% zinc is not much more effective. So we have to go a higher percentage of zinc if we need a more ductility, but strength is expected to go down. So we have to see that what is our requirement, and then accordingly we can replace aluminum, certain aluminum by zinc to get to improve certain ductility, but reduce the strength when you are adding the zinc. So here our finding is that calcium is no effect. Calcium is a similar effect as the aluminum, and that is not advisable to use in this magnesium aluminum alloys. Zinc is you can certainly you can use some percentage to reduce your brittleness, and and then you have to optimize the aluminum and zinc according to requirement of your strength as well as ductility. In the case if you want to use the zinc, but our actually the aim is not completed in this study, so that's why we have here you can see the fracture surface. Also here the pure magnesium, what I mean, you are seeing that this is a completely brittle fracture, kind of brittle and mix of the like ductile and brittle type of fracture. But the aluminum, when you are adding more or more going to brittle, this you are see that this is the intermetallic phase, which is region where this become a completely brittle. So and that's why it is a failing at a very low ductility. And then when we are adding calcium, you can see that the calcium is a more brittle, and also here you are not solving any problem. But in the case of the zinc, you can see that this ductile region is increasing, and still there is some region of the brittle region. So it is a mix of the ductile and brittle. So that's why you are getting a moderate strength and moderate ductility in this case. So actually, our purpose was there to reduce the gamma phase and increase the strength. But in this case, we have seen that we could not able to increase this strength. But we just only moderately we can use the zinc to make the alloy and to moderate strength and moderate ductility. So,
Sir, I have one question in the previous one, sir.
yes.
This three alloys, what we have developed: aluminum, magnesium, aluminum, zinc, and magnesium, aluminum, calcium. So, this all findings were for primary process, no, sir. No secondary process has been done on these alloys, like rolling or forging, like that. Secondary process.
No secondary processing was done,
Okay.
because the when there is a brittle, when you are if you go for a rolling or a forging, your sample will be cracked, and further your property or your component cannot be sustained, because if your material is brittle, if you applying a forging, then material will become a crack itself. Many cracks will form. So that's why we have not gone for secondary processing. But in case of magnesium, aluminum, zinc, you can secondary processing can be done. Yeah, that was not done in this case.
So, by doing that, any further improvement in the property can we expect?
Yeah, that can be expected in the
Okay.
case of magnesium, aluminum, zinc.
Yes.
So yeah, I will show you the in case of aluminum in later slides the forging effect of forging.
Okay, sir.
So,
Yes.
but here our aim was to reduce, increase the strength. That was not actually improve the, because in powder metallurgy we have improved the strength around 2 to 3 times. But in case of the casting method, simply by using aluminum, zinc, and calcium in magnesium aluminum alloy, we could not able to achieve that one. So that's why another method, rare earth, addition of the rare earth elements was done in this magnesium aluminum alloy, because the rare earth having property to combine with the aluminum, form another intermetallic compound, and rare earth also reduce the grain size of this magnesium, and so that's why it has a very means a strengthening effect in this case of magnesium. So that's why we have used this rare earth element in in this one. But rare earth element is a very less percentage. Rare earth element to increase the cost of this alloy, but we are using 0.1, 0.2, 0.3 percentage. So that's why it not actually affect the much increase the much cost much. So so here you can see the what is how the effect of the rare earth. Actually, this rare earth element increase the nucleation, and that's why it improve the reduce the grain size, and grain refinement is taking place during the solidification. And it is when the grain is refined, so obviously your mechanical strength will be increased, and because this it also improves your metal quality, and reduce the impurity level. So that's why the creep strength of this alloy and this intermetallic, which is forming, which is stable at a high temperature. That's why the creep strength of this alloy is also increased, and rare earth also improve the corrosion strength. So that's why rare earth having a very good effect in magnesium aluminum alloys. So actually, main problem was this gamma phase compound in magnesium aluminum alloys, and this gamma phase is coarsening when you are heating the alloy in this range, this 393 to 400 degree temperature. The gamma phase become a coarsen, and further your property deteriorates. And this gamma phase, which is intermetallic and a cubic structure, which is not compatible with this magnesium HCP structure, and interface become a fragile. So these problems by using rare earth elements, actually rare earth elements is more reactive to aluminium compared to the magnesium. So this magnesium aluminum rare earth element first forming intermetallic compounds, this aluminium 11 Re3, and it is incoherent with HCP matrix. So it is coherent with the HCP matrix, and its melting point is also high, so that it cannot be melt during your operation 300 to 400 degree temperature. So that's why it is also increase the keep resistance of this alloy. Here you can see in this diagram, when rare earth element was, this is the without rare earth, and then when you are increasing the rare earth element, your creep property increases. So here you can see 300, 400 degree temperature, creep rupture strength is increasing. How this alloy we have made, here you in this schematic diagram, you can see the magnesium cerium we have added in this one, this cerium 1%, 3%, and 5% to in this alloy to see the effect of the cerium. And you can see that we have taken this first magnesium cerium master alloy, and we have remelted it and homogenized this alloy for making this master alloy. And then magnesium melt was taken, and in the magnesium melt this master alloy was added according to your composition requirement of this range. And then this was actually cooled in a copper mold casting, so that in copper mold very high cooling rate, so that the grain size is very low. And then we have studied the microstructure and mechanical property of this alloy. So here you can see the microstructure and the X-ray diagram. So XRD, you can see that this how the different phases are forming this magnesium 17 aluminum gamma phase, which is there in pure magnesium alloy, magnesium aluminum alloys, and the gamma phase is this one is reduced in 1%, but in 3% it is completely gone, and in the 5% you can see the another intermetallic. In the 3% there was a Al2Ce phase, and in 5% Al2Ce and magnesium 17 cerium 2 phase is forming. So if you are going higher cerium percentage, the another phase is forming, this magnesium 12Ce, magnesium 17 Ce2. So in the microstructure also you can see that this is the magnesium aluminum matrix phase, This one is the Al2C phase, this bigger one polygonal type structure, and then you can see Al2C phase, and this one flaky phase is this one magnesium elements. Actually, this is the a magnesium 17Ce2 phase. It is wrongly mentioned here. So in case of the high percentage of the cerium, and you can see the phases distribution in this image, and after that here you can see the mechanical property. Mechanical property, this is the magnesium aluminium alloy, this magnesium 10 aluminium, and this is 1 cerium, 3 cerium, and 5 cerium. So you can see that by adding cerium, you can improve this ductility. It was earlier, it is around 15%, but it is going around 25%. But if you are increasing cerium further, you are reducing the ductility. So if you want to having a high ductility around 25%, then you can use only 1% cerium. But here strength is little more compared to the magnesium aluminium. But if you want to increase the strength further, you can improve the cerium percent around 3%, but here density you are getting around 17 to 18%. And when you want to only increase the strength, you don't concern about the ductility, then you can go up to cerium around 5%. So in this case, you are getting a strength around 450 megapascal, and but the ductility is almost same whatever it was initial. So it depends on your requirement, design requirement, and component. What you are looking for the final component strength. You can go and design a component according to this by varying the cerium percent according to your requirement. So after that, we have also added, apart from cerium, we have added this neodymium percentage in this magnesium aluminium alloys. This similar method was used here. So in this, we have first prepared the master alloy, and in master alloy was added the magnesium melting. Here we have used stir casting method, and then magnesium alloy ingot with this neodymium we have got. Here also you can get the different phases, as it was because the rare earth almost we having similar in nature in different aluminium and magnesium alloys, and you can see this is the 1ND. Here it was magnesium 4 aluminium, where this phase and was refined. It is totally, you can see this gamma phase which is along the grain boundary, but here it is refined, and this is along the grain boundary, and some within the grains are formed. But if you are increase the neodymium percent to 4%, you can see there is another intermetallics are forming. So it is like a branches structure, polygonal type triangular structures, and so after that it is, and you can see how it is homogeneously distributed in this magnesium aluminium matrix, and the XRD also showing this phase. So, and when you are adding the gamma phase, this your ND, your gamma phase is completely disappear, and two new intermetallics, your Al2ND and aluminium ND3 forms, and morphology of the intermetallic changes with increasing neodymium, because it was a point shape this phase, and dotted you can see like a dot, and when you are adding more neodymium, the morphology changes into like a branch structure. and polygonal type structure. So here you can see the hardness, how the hardness increasing with this neodymium percentage, and this is the fraction of the this intermetallic phase distributions in this one, how the phases and their different sizes varying in this, adding this intermetallic part, forming the intermetallic neodymium, adding neodymium and forming a Al2Nd and Al11Nd3 phases. So this aluminium neodymium phases increase the strength as well as reduce the grain size. That's why we are getting a strength and hardness here, which is also indicating that strength is also increased in this adding neodymium. And then this post-it after the casting, the post-heat treatment also has been done. So here we have solutionizing this above 400-degree temperature and then kept certain time and then cool it to a room temperature, and then aging was done around 177-degree temperature, and then it again cooled to the room temperature. The logic is that we have taken the alloy from room temperature, and then we have gone to the complete liquid semi-solid region, and from semi-solid region we have again come to the two-phase region after the aging. So here you can see the different times of the aging, how the microstructure is changing. This is the magnesium aluminium. 1Nd, this is 1Nd, this is 1Nd alloy with, and this is 4Nd. Top one is the magnesium 4 aluminium 1Nd, and bottom is the magnesium 4 aluminium 4Nd. So you can see that the your different aging time. This is the before aging, and this is 24-hour aging and 72-hour aging. So you can see that the aging, your precipitate size is increases. Here you can see your precipitate size increases, intermetallic precipitates, and in 24 hours it was there in somewhere distributions was somewhere agglomeration. So here it is distributed uniformly, but when you are increasing above 24 hours, is further the size of the intermetallic precipitate are increased. It shows that it's going to be overaged. So here you can see this aging graph, and the hardness was taken different aging time. So you can see the after, this is the 24 hours time. After 24 hours, again the hardness is decreasing drastically and then become saturated. So from the microstructure, it is also showing that when you are going above 24 hours, your particle size become a coarsening, get portion. So that's why your strength hardness is decreased. So here we can see that this optimum aging time is around 24 hours of this alloy. And the hardness drop after peak aging, it shows that the material got overaged after the 24 hours of the aging time. So now I'm going to show that the forging effect of this alloy with this cerium in aluminium alloy. Actually,
Before this, sir, sorry to interrupt you.
Yeah.
In the previous slide, sir, we have discussed about the optimum aging time.
Yes.
Can you, sir, optimum percentage of mixing of this aluminum and neodymium here, which will give the better optimum result? That I think
Yeah. You are telling about this aluminium.
Yeah. Here we have added 1% and 4%. So which one is optimum, sir? We have to go for, if this aluminum we alloy we have to use. So or in between that we have to again search it for better one.
Actually, here we have prepared this alloy for this HAL Koraput. So the HAL Koraput main requirement was to for a gear housing box. This alloy they mostly interested are our application was to improve the creep resistance of this alloy. So creep resistance is depends on the your intermetallic or how much stable at the high temperature. So in this case, actually, in the 1% of ND, we didn't get a intermetallics high volume fractions. We are getting gamma phase some and some intermetallics, but volume fraction are very low. But when and the shape is pointed, so its creep resistance was not increased. So we have gone to from 1 to 4%, and in 4% it was found that it is very good. But in between, actually, we have studied our for the creep resistance. So creep resistance increasing, but in the 3 to 4% we have found better creep resistance. So actually the data is not shown here, please. So, but in for the creep resistance around 3% to 4% we have found that better creep resistance because of this intermetallic, more intermetallics and the branching of intermetallics, which is makes this alloy a high thermal resistance, improve the thermal property, and this intermetallics are stable at that temperature between 300 to 400 degree temperature. So that was the requirement. So that's why we have not actually focused on the strength part of this alloy. We have focused on the creep part.
Creep resistance part.
Yeah.
Thanks.
So any further question on this part?
Anybody from the audience, participants?
Okay, so we can go for the next one, where actually we have used this Aluminium 7075 alloy for a high strength application. So here we modify this 7075 alloy by adding with cerium. You can the cerium 0, 0.1, 0.2, 0.3%. We have changed percentage of cerium to see the effect of the cerium in this 7075 alloys. This alloy was also made by similar method. We have prepared the aluminium cerium master alloy. Then this alloy, master alloy added in aluminium melt and then homogenize. And then we have done casting and then hot forging. Hot forging was done of this cast samples. And then solutionizing, aging, and then final microstructure and mechanical property was studied of this alloy. So we have done the melting around 780 degree temperature and casted this alloy, homogenized for 54 hours. Forging, for forging we have heated the sample 400 degree temperature, and then forging was done. So forging actually continue up to 250 degree temperature. So in this range, 400 to 250 degree temperature, the open die forging was done. So it is you can see here the press and the samples are forged in this one, and finally after forging you are getting this shape. And then solutionizing are 470 degree for 2 hours, and then aging. Actually, we have done double aging. So 107 degree temperature for 6 hours, then 177 for 6 hours, and air cooled then. So here you can see the microstructure. So this is the Al2COMG, this phase, and then Al4C, and this is Mg32 aluminium zinc 49. This is the eutectic type of phase and mixed complex phase, and this MgZn2 and alpha magnesium. These are phases are mostly forming in this alloy. So here you can see this is the microstructure of this, where we are increasing from cerium 0.1 to 0.3%. This is 0, 0.1, 0.2, 0.3%, and actually the alpha matrix was surrounded by the intermetallic secondary phases, and this cerium addition, you can see these continuous phases are broken, and a gangular type of the alpha dendrites are forming. So this is the optical microstructure, and then in this after forging and aging, you can see which is the your phases here are continuously along the grain boundary, this interdendritic secondary phases, which is here you can see this is the magnesium aluminum 0.1 cerium 0.2 0.3. This interdendritic particles are broken and completely which was along the grain boundary. It is not in the along the grain boundary. It is homogeneously distributed grain boundary inside the grain everywhere. And in TM microstructure, you can see that this Al4C phase here in this one Al4C phase, how it is distributed. You can see this is the after this increasing the cerium phase, this particles intermetallic phases shape also changes. So it was
black spots, sir.
yes, this black spot.
The size is also changing, sir.
The size and the shape
also.
And it is very uniform, very fine particles,
Right.
and around 5 to 10 nanometers in the size. And when you are adding this cerium, the increasing your shape and size also changes. Earlier it is a 10 to 20, but when you are adding more and more cerium, then your phase shape is changes and the size little bit increase. And this, you can see the tensile strength. Tensile strength. This one is a yield strength. Yield strength, and this is tensile strength. So it is 0.4% cerium, and the ductility elongation, you can see your this one elongation is yeah, it is there, and your tensile strength increasing, and after that it is going to saturate after 0.4%, and ductility almost remains same, and after that if you are going to 0.4% above 0.4%, it is decreasing. So we found that the around 0.3 to 0.4% is optimum cerium percentage for this this alloy, and the Young's modulus also little bit improved by this adding cerium percentage in this alloy 7075% alloys. And mechanical property, we are getting around strength around 560 to 550 megapascal, which is quite good for this 75 alloys. So to summarize the talk, we can say that there are a broad demand of the lightweight alloys for aerospace and automobile sector, and the magnesium aluminum are found for this lightweight applications, particularly in case of a automobile and some like a gear housing box for a aerospace material, aerospace application, and this in the cerium percentage rare earth element in this alloy. And rare earth elements not only improve the mechanical property of this alloy, but also improve the creep resistance of this alloy, so that these alloys can be improved, can be used for a different high temperature applications as well. And this case study which we have seen that this alloy can be designed as per the requirement of the component or requirement of the application-oriented requirement. So these alloys can be modified, and the processing can be also checked or changed according to your requirement. And you can optimize the property. You can choose the secondary processing method, or you can go for this heat treatment method, or you can go for forging method. So depends, and aging depends on your requirement of the final property. So this with this I thanks for your patience hearing, and if any questions, yeah, you can.
Thank you, sir. Anybody from the participants want to ask a question? Actually, sir has given a very wonderful lecture on lightweight alloys. I think many of us are working on this aluminum alloys and composite. So, any kind of doubt if you have, I have seen Mr. Bhubaneswar Prasad, faculty from CIT. I think he is working on aluminum 7075. Mr. Bhubaneswar Prasad, if you have any doubt on aluminum alloy 7075, you are working in this alloy. Bhubaneswar?
There is some people have raised the hand, so either you can go by.
Bhubaneswar Prasad, yes. You can on your mic, Bhubaneswar.
His mic is, I think, is not. Yeah, now.
Yes, good morning, sir. Am I audible?
Yeah, you are audible, Bhubaneswar. Yeah, if you have any question
Sir,
about
I am
7075.
on this, sir, I am working on this topic, but my role is different.
Okay.
Yeah,
Can
you
introduce
have
from
So
where
I'm
you are
facing
working.
problem. I'm facing not too much problem in between the machining and other testing during the other mechanical properties. So it will work very good in machining.
No, first of
And
all, you
sir,
introduce yourself, ki in which area you are working, and right from beginning, and then give 1 or 2 minutes time to introduce your project. Then only sir can suggest you something.
Sir, I am working on the aluminum 7075 alloy with nanoparticle of silicon carbide.
So you are adding in, silicon
So I
carbide.
am preparing the sample with casting, stair casting, and preparing the sample for the testing of tensile, micro hardness, and other TEM and SEM.
So
It's in working phase, not it is completed. It has been not completed till now. I am doing work on this.
Okay.
So, have you any problem, or have you analyzed the interface of the silicon carbide with this aluminum 7075? How it is behaving interface?
Yes, sir, I have a problem regarding this because silicon carbide is not too much penetrated in the aluminum 7075. Whatever I found in the optical microscope,
The mixing problem is there.
So
yeah, there is a mixing problem.
your agglomeration, you are getting agglomerated.
Yes, sir.
Agglomeration problem you can reduce a certain extent if you can preheat your silicon carbide before adding the melt, and second one, you actually reduce the melt temperature to a semi-solid region, and add your silicon carbide particles, and then stir for a 1 or 2 minutes, and then further raise your temperature to go for melting, melting and plus 50 to 60 degree above the melting temperature, or 100 degree, and then you again stir. So in that case, you can reduce the agglomeration problem in this case.
Okay, thank you very much, sir. Thank you.
Semi-solid region, your particle will be distributed and fixed with this magnesium, homogeneously mixed. And another further, there is some agglomeration if you are going to further increase the temperature and going to the clear liquid condition and then again melt. So that's why then liquid agglomeration that can be also removed.
Okay,
So,
sir, I will do on this.
Yeah, so
Okay,
you
thank you.
try in this method, means initial adding your particle in semi-solid region, because if you do adding liquid region, it will be somewhere agglomerated. But in semi-solid region, once it is fixed with this alloy, this aluminum, then further it not going to agglomerate. And you also preheat your powder, because sometimes your powder will be having moisture and it will not separate it to each other.
Of course, I did not preheat the nanoparticle. I mixed directly nanoparticle.
That's not the problem.
That
So
was the problem. Yeah, of course.
try and see that if any improvement, I think you can get it. So you are adding silicon carbide nano or a micron size?
Both nano and micro, both I have done two casting. One with nanoparticle and other with microparticle.
हम उसमें कुछ बोलेंगे तो ये सही नहीं है। क्यों बोलेंगे जब मेरा कुछ इधर उधर होता।
Okay, so you try in this method.
Okay, thank you, sir. Thank you very much.
Okay, thank you, Bhattacharya ji. Manisha madam, you want to ask a question?
Am I audible, sir?
Yeah,
Yes.
you are audible, madam. Yeah.
Yes. Okay. Sir, I have a question regarding applications of magnesium alloys in automobiles and vehicles. Sir, one of the drawbacks of magnesium alloys is their machinability. Since during machining, they can get ignited suddenly, leading to fire. Then, sir, what are the alloying elements that can be added and how they can be used, sir?
Yes, if you are using pure magnesium, then these problems will come. But after alloying, suppose if you are alloying with the aluminum or other elements, then this ignition problem during machining, we have not faced such a problem, and this problem can be reduced, because in pure form it is ignited. So
okay.
Yes,
Sir, aluminum and cerium can be added and they can be used. Okay.
yes, aluminum and cerium,
Okay.
yes, we reduce this
Okay.
problem, and same time this strength also can be improved.
Also, we can replace the heavy metals like iron in automobiles with these alloys.
मशीन का पार्ट्स वगैरह बनता है, आखिर वो सब तो एलॉय ही रहता है, तो सब की जानकारी तो कहाँ से मिलेगी?
हाँ, क्या आप क्या बोल रहे हैं?
नहीं, जो आज एफडीपी में जो चल रहा है एलॉय वगैरह के बारे में,
हाँ,
तो वो सब चीज का जानकारी, आई थिंक बेसिक जानकारी तो केमिस्ट्री से ही ना आएगा सर।
हाँ, बेसिक जानकारी तो आपको केमिस्ट्री से मिलेगा ही।
देखिए यही बात हम बोले अभी, देखें बोला बेसिक जानकारी तो केमिस्ट्री से ही मिलेगी।
बेसिक जानकारी तो आपको केमिकल, बिकॉज दीज आर द एलिमेंट, भी तो केमिकल एलिमेंट्स हैं, उसका रिएक्शन तो आपको केमिस्ट्री से ही मिलेगा कि कौन सा रिएक्शन होता है। बट जैसे उन्होंने पूछा कि ये आपको जो फायर कैचिंग आइदर मशीनिंग टाइम में, तो अगर आप एल्युमिनियम को अलाइन करेंगे या तो ये इंटरफेस पे जो मैग्नीशियम के ऊपर में एल्युमिनियम रहेगा तो वो फायर कैचिंग नहीं करेगा। अगर प्योर मैग्नीशियम रहेगा तो वो फायर कैच कर सकता है। बट वो जब मिक्स हो जाएगा एल्युमिनियम से, तो देन आप मशीनिंग टाइम में जो सरफेस टूल के कांटेक्ट में आएगा और जो सरफेस एक्सपोज होगा ये फायर के उस पे, तो एल्युमिनियम सरफेस पे रहेगा, तो दैट्स वाई वो ये फायर कैच नहीं करता। तो एक मतलब सरफेस पे एक ये करता है, लेयर टाइप फॉर्म हो जाता है मैग्नीशियम एल्युमिनियम।
Okay, thank you, sir. Thank you very much, sir.
Thank you, Manisha madam, for asking this good question. Sir, machinability is the big problem for alloys. Any other participants want to ask? Any person? Anybody from South India? Dr. Akhilesh Kumar Singh is there? No.
Any question in chat box?
In chat box, is there any question? No, sir, I think they have understood the thing. So, if at all you have any doubt in future, you can contact to sir on his mail ID, and to me also. If you have any question, you can put me. I will forward the question to sir, and hopefully you will get the answer.
You can mail to me the question if any doubt further, and answer in the mail.
We'll get you'll get the answer. So anybody working in this aluminum alloys and composite materials, so any kind of doubt, any kind of suggestion, if you want, you can ask to sir. Thank you very much, sir, for giving such a wonderful talk on lightweight alloys. We are enlightened with knowledge of lightweight alloys, and we have seen if we go for iteration of adding the percentage of elements. So what will be the pros and cons, and how the structurally or mechanically we can get a good alloy out of them. So thank you very much, sir, for giving your precious time for us in this 5 days lecture, 5 days workshop on faculty development program in manufacturing and automation. Today we are third day, and thank you very much, sir. Any suggestion you want to give, sir, for better improvement of this program, or please, sir, you can say, suggest us.
Yeah, thank you, Dr. Arvind, for a nice arrangement of this faculty development program. And yeah, actually, because of the situation, we are doing this program through online. So in online, is always limitations. The interactions are limited. Yeah, but in future, if the situations are improved, in future you
Definitely, sir. We'll meet offline, sir.
offline.
Yes,
Yeah, offline will be a better interactions, and the participants can clear their doubt, because in online sometimes the people are also not listening or giving attention to the lecture so much. So yeah, so but in offline there is a chance their physical interaction will be much more better.
Yes.
And this is a very good in mechanical engineering, mostly people are working on the composite material. So the alloy, because in metallurgy background is a little bit required for the alloy development, but the most of the people in mechanical engineering, they are having background of little bit metallurgy, but they are preparing to work in the machining and designing, tool designing, and also the composite material. So there, I see that most of the people they are working in the composite material. So the composite and the alloy is also pre-required, because they are using the alloy and adding certain reinforcement in the alloy. uh, Improve the property as per their requirement. So in the composite, the reinforcement selection and reinforcement distribution, and the actually the interface of the reinforcement with the matrix phase, means alloy, whichever they are taking as a matrix. So in that case, your LOI knowledge also is required, so that you can better understand that the how reinforcement should be added in this LOI, and how the reinforcement will behave in this LOI, and whether the interface of the matrix and the reinforcement are good, because the ultimately your material should behave united. If your reinforcement behave another way, your matrix behave another way, then you will not give your homogeneous property, and the material will fail in before premature failure. And so that's why in composite also the interface of the reinforcement and the matrix is very important. And to improve the interface, the people have adopted many techniques to code the reinforcement with this matrix phase before adding the reinforcement in the matrix, and also to improve the surface area of the reinforcement, so that the more surface area will be in contact with the matrix, so the property can be improved. So there are many techniques, and in the that can be also it can be learned with this alloy. In LOI, actually we are forming a different phases, which is a in situ formation. But in composite, we are adding extra in situ composite are also there, but in the mostly the composite we are adding extra reinforcement from outside. So that is the only much different. But after that, the property study and the nature of the microstructure and how microstructure changes will affect the final property, or your intermediate property, that also matters. So the alloy property is actually study of the alloy is more help in for the further composite preparation.
Thank you, sir, for your good
Yeah.
suggestion.
So yeah, thank you.
I would like our principal sir to say something on this, sir. Just a second. Principal sir. Principal sir, are you audible to us? Yeah.
Thank you very much.
Sir, I'll introduce
Chaubey ji.
our principal, sir, Dr. T.K. Das. He is our principal of our institute. And principal, sir, is Dr. A.K. Chaubey, senior principal scientist at CSIR-IMMT, Lucknow. IMMT, Bhubaneswar.
Bhubaneswar.
Yes, sir.
Yeah, good morning,
Uh,
sir. Nice to see you on the screen. So actually, the morning we could see you. So you might have busy in different yes responsibility. But thank you for joining, and I hope you might have seen some part of our lecture also. So, sir, any comments, sir?
Chaubey ji, namaste. Actually, I am associated with IIMT Bhubaneswar for number of years. Actually, when I was working in Steel Authority of India Limited. Actually,
Yes, sir.
Biswal ji ke sath we have worked.
Yeah, Dr. S.K. Biswal.
Dr. S.K. Biswal, and Mr. Tiwari is also was involved. Yeah, your institute
Yes,
is very good actually, and having lot of infrastructure. And definitely you have lot of research experience, and from that our faculty members definitely got enriched your lecture. I think faculty members also can give some inputs, but already I think a lot of questions they have asked you, and
yes, sir.
matter
Yes.
was discussed. So,
Yes, sir.
your topic was on material science, no?
Yes, lightweight material for automotive and aerospace application.
Aerospace application.
Yes, sir. So
Is
you are,
your-
sir, basically you are associated with Dr. Biswal, so you are
yeah, I am a
side.
mineral. I was looking after the coking coal and its derivatives actually.
Yeah, yes, sir, yes. Oh, so he was actually he is now retired. So Dr. Biswal last year he retired. So he has opened some industry in Bhubaneswar. Also, he was still he has joined some industry after retiring.
No, that's good. Actually, he has very good experience and initiative also.
Yes.
So definitely that will be helpful in teaching or giving output to industry. We are really thankful to you. Thank you, Chaubey, and definitely in future also we will be getting your support or wherever we require your help. And maybe we will be also looking for, in case some students or our faculty members carrying out certain research activities, they may get help from your laboratory.
Yes, sir, definitely. Any help required, we will always help, sir, if any. And thank you you for giving this opportunity to present my work. So I hope that faculty members also have got some input, and they might have some this will helpful to their future work.
Thank you, sir.
I'm thinking, seeing that attendance is about now 54.
Yes.
Hopefully attendance was and Jayaprakash ji, आपने वो day wise attendance रख रहे हैं क्या? You are keeping attendance.
Yes,
Who
sir.
are
We are
all
yes,
attending?
sir. We are keeping, sir. We are keeping.
So today, what was the maximum attendance?
Amrit, sir. Now I am saying it's a.
अच्छा ठीक है, I think Arvind ji actually
So we have downloaded it for some time to time, and we,
not only download, आप एक बार communicate भी कर दीजिएगा participants को that वो जो participant registration किया है how many days he is attending, how many classes he is attending.
Okay,
So
sir.
ये थोड़ा essential है because it is online. No, we are not very sure कितने attentive है. Faculty भी थोड़ा नाराज हो जाएंगे अगर बहुत ज़्यादा attendance नहीं है. So and his purpose, देखिए, his satisfaction level will not be that good if less attendance is there. ये थोड़ा देख लीजिएगा. Anyway, thank you very much, and participants also. I am thankful that you all are attending seriously, and hope you are getting enriched from different experts. Chaliye, thank you very much. Okay.
Thank you, sir.
Okay, you can.
Thank you, sir. Thank you very much, sir. Thank you, Chaubey sir. Thank you, Principal sir. So we'll end up the session now. Thank you very much, sir.